and thanks for having me, everyone. So I'm Jason, and Randall's over there in one of the other boxes. And yeah, so we'll be talking about, let me pull up the presentation. Everyone can see that? Yeah.
Yeah.
Awesome. So we'll be talking about robust forecasting using random reservoir networks. And this is forecasting as in dynamical systems forecasting. So that could be geophysical or biophysical applications, or I guess industrial applications as well. And then random reservoir networks is talking about reservoir computing. And so I'll give some kind of introduction to that if you guys haven't heard of it before, and then talk about some finding hyperparameters and such. And then Randall will talk about more specific applications of that. So change the slide. So because I'm talking to the INC here, I wanted to motivate some kind of biological basis for why we would want to forecast using random networks. And so because of that, I'd like to note that there are examples of biological networks for which are, I would say, functionally random. And the example that sort of led me actually to reservoir computing is that of the insect olfactory system, which is the network that identifies odors in, say, honeybees or locusts and other insects. And so the network kind of goes as, we've got these olfactory receptor neurons here, which read in your chemical signal. And then these convert it to an electrical signal, which go to the antennal lobe, which pre-processes those signals and converts them to some kind of spatiotemporal pattern, which then go to the mushroom body, which learn those patterns through spike timing plasticity. And so the part that I just wanted to mention here, kind of briefly, is that the antennal lobe works through a process, or the activity can be described through a process called winnerless competition, which is a property of large random networks with asymmetric inhibition between them. And so despite all the kind of biological messiness here, there's sort of projection neurons, local neurons, structures called glomeruli, I would say that this is functionally random because the mathematical structure underlying it can be sort of approximated by a large random network. And so just to kind of motivate the observations such as this led Maas and Jaeger in 2001 to independently propose the idea of using random networks for forecasting and classification. So that's kind of some kind of biological basis. Also, I just wanted to say that in physics, it's generally the rule that if you have a question, you can just kind of shout it out. I know that's not necessarily true in biology, but don't wait till the end of the talk to ask questions. All right. So now that I've kind of introduced or motivated maybe what led me and some other people to work on this, I want to describe what a reservoir computer is, and then I'll talk about what it does. So it's a form of recurrent neural network, and there are a number of definitions floating around there, I know. But the one that I find most compelling is that a recurrent neural network is a network that depends on its previous state. So it's a dynamical system. And this is in contrast to maybe what you see in like other kinds of machine learning, like feed-forward networks or a multi-layer perceptrons, which act more like functions. So they take some input and then put in an output, but they assume the statistical independence of those inputs. It doesn't matter which order it goes in, whereas recurrent neural networks, it does depend on the order because it depends on a previous state. And that's why it's sort of natural to look at these things for time series prediction and forecasting, which is what we're going to apply this to. So architecturally, the network consists of a kind of a large fixed random network. That's the main processing center. And these are fixed connections. And that's a major point. So we don't train this large fixed random network. And these nodes here can be things like hyperbolic tangents or other dynamical nodes. We've put Fitzhugh-Nagumo neurons in, Hodgkin-Huxley neurons, those kinds of things. But the idea is that we put in some input, we have this random network, and then only the final layer is trained, so this readout layer. And this can be like a linear regression. That's what we tend to use, but it could also be a support vector machine, something like that. And the idea is that if you take in an input at u of tn, you want to predict u of tn plus 1, right? And so then what you can do is then loop this back around, and this becomes kind of a forecasting machine. So a little more mathematically, we have some input data u, and this is generated by some vector field f of u here. And this is a dynamical system, but we don't need to know what generated this data. It just has to exist. It needs to be basically statistically stationary, or to have been on some attractor for us to be able to forecast properly. And this is a dynamical system because, right, the derivative of u here with time is dependent on some function of u. Right, so we don't know what it is, but we assume it exists. And so we take this data u here and we drive our reservoir computer with it. So this is now our reservoir computer is a driven dynamical system because it depends both on r and u. And then training then consists of taking r for the entire sort of driven trajectory of the training data and finding a function phi such that phi of r is equal to u. And then this is our loop backwards because we can just replace u with phi of r and drive this forward in time. So this is now an autonomous dynamical system, again, instead of a driven one, because it's no longer dependent on u. So the idea is that if phi were perfect here, we could basically have an exact reconstruction of this driven system and drive it forward in time and be able to predict exactly what u is for, you know, the rest of time. So are there any questions on how, or like the construction of a reservoir computer?
I have one. How would you implement the phi there? Would it be like, would you just have an output unit with phi as like the activation function, or how would you do it?
Yeah, so it can be done a number of different ways. What we tend to do is just use a linear regression. So we have phi is actually some matrix multiplied by r. And then we find those parameters in phi through linear regression. But it could also be, you know, you could train a simple like 2-layer feed-forward network or something like that as well, or a support vector machine. All right, I see some hands, I think. Avanish, did you have a question?
I did, but I think I understand a bit more. So I was just trying to get more of an intuition as to the structure of the random network, if there is any, yeah.
Yeah, I'll give a concrete instantiation a little later of exactly how we do it. But basically, it's some kind of adjacency matrix, sort of mixing the terms of R here, which is a vector.
Right. Should I have an intuition as to what you're trying to do with the random network?
So the next slide, I'll show and sort of how we apply this. I don't know if that answered your question.
I guess I'll wait until the next time to find out. Yeah.
Right. Oh, I think maybe the idea is that I want to get across is, so U is some sort of small or not so small d-dimensional vector, right? Which is telling the system. And then this is projecting it into this really large space in this random network, which is then you can read that out into sort of the next output. So there's some kind of mapping there.
Okay, I think I get a bit. I'll wait for a bit to see if my intuition is correct. Thanks.
All right. I saw another question. Was it?
I was going to ask another kind of clarification related question, but I think maybe I'll wait till the example as well.
All right, sounds good. Yeah, so an example of how we would use this, right? The problem we're trying to solve is mainly chaotic time series prediction. Those are the examples that we're going to give. And this is important traditionally in, say, geosciences and engineering, but could be useful in other fields as well. And so the reason chaotic systems are really hard to predict is because small perturbations in initial conditions will diverge exponentially from each other here. And this divergence is given by kind of numerically by the largest Lyapunov exponent, which is λ1 in this exponential. And this governs the level of chaos. So if λ1 is positive, then you have a chaotic system, right? If it's negative, then you won't get that exponential divergence. And so it's non-chaotic. So λ1 kind of is a hallmark of what is a chaotic system. And so a concrete example here is the kind of famous Lorenz Attractor. And a lot of the examples I'll give today are from this, because it's kind of, you know, what we physicists call the hydrogen atom of the system. So the hydrogen atom is like the simplest possible atom, which we proved all these theories on. And so the Lorenz system is a sort of good test bed for that. And it's a simplified model of the upper atmosphere is what it really is. But usually I just think of them as wiggles. Right, so this is an example of a reservoir computer at work. So the left-hand side here, so we've got X, Y, and Z in this three-dimensional system. And this would be the end of the training data. And then we basically train on phi, we find our function phi, and then go and evolve the reservoir computer forward in time along with the original system, just to check, you know, how it's doing. And we see that it predicts really quite well up to a certain amount of time. And this is just generally what happens in chaotic systems here, because of this exponential divergence. So there's always a limit to the amount of prediction you can do. And I just want to note that λ1 here gives kind of a natural time scale of the system, because it's in sort of an inverse time constant. And so this gives good predictions to something like 7 or 8 Lyapunov times in this particular example. And so what this shows, and I just wanted to show this, is that reservoir computers are a very powerful technique for forecasting for dynamical systems. But there are a couple problems with them, and that's what we'll be getting into later. The first one is that they are quite sensitive to hyperparameter selection. And so we want to give an idea of how to select those hyperparameters such that you can apply this to new problems without like a huge computational cost, especially when you scale up to larger and larger systems. And then two, it's that they often give non-physical predictions, or they're not robust. And so that's another issue that we'll be addressing later in the talk. So did this kind of clear up some questions people had?
I was actually going to ask relating about the any kind of feedback connections from the output to the reservoir. If you've ever, if the model includes that at all. But I'm guessing by the diagram that's not the case.
The feedback connections from what?
From the output to the reservoir for during training.
Right. So the feedback connection is only for the forecasting stage. So if we go back here, right? So this feedback, what you do here is you take the input and you give a prediction, or you have your reservoir states like over time during the training, and then you find that function phi afterwards to predict, to minimize the distance between this and your prediction here. And then you loop it back around.
Right. Yeah, because I've actually seen it though. So I just want to clarify, because I've seen some implementations where there is directly feedback from the output to the reservoir for training purposes. So I just wanted to clarify that that was not the case.
Yeah, that's not the case in this formulation.
Thank you.
All right, so just to recap, this is kind of the setup. So we've introduced reservoir computing as a powerful way to perform dynamical systems forecasting. And now we're going to look at sort of problems with applying these to new problems, to bigger problems, and then hopefully gain some intuition and guidance on how to fix those problems. So the first issue I'm going to talk about is that these are very hyperparameter dependent. So if you remember the basic architecture, this is now a specific implementation of our f of r. So this has a number of hyperparameters. So gamma gives our kind of time constant. We've chosen hyperbolic tangent to be at the nodes. A is the adjacency matrix. So this mixes the R's together. So this is kind of the implementation of the large random network. And we choose A to be random, but we choose some hyperparameters for it. So the largest eigenvalue, which is called the spectral radius, the density of the matrix, so like how many nodes are non-zero, how many connections are non-zero, and then of course the size of that. And then we'll also have the strength of the input, which is given by sigma. So these are just examples. This is just one specific implementation of a reservoir computer. But if we look at the sort of two-dimensional slices through parameter space, we see here, this is one parameter, say the spectral radius, this is gamma, this is sigma, this is the density. And you see a kind of island of red good predictions surrounded by a sea of blue, which are the bad predictions. And this of course gets more and more complicated as you get to, these are just two-dimensional slices. So if you're in 4 or 5, 6-dimensional space, it's a lot harder to find those regions. And so searching for this is computationally intensive. What people usually do is do kind of a grid search over it. And each time you have to train the reservoir, you have to look at it, you have to, you have to then forecast over a number of points, see if it's good prediction, and then move on. So that's the problem. Questions on the problem statement?
Can you explain again what's the difference between alpha and beta here?
Oh, yeah, so sorry. Alpha and beta, this is just summation notation. So this is, say like this is R, this is the first vector in this, dr1 dt, right, equals gamma minus R1. So I've just indexed the vectors. So this is like a matrix vector product. And same with this. So you're summing over repeated indices. Yeah. Any other questions? All right. So
then I have a more general questions. Like there is like a fading memory, right, on those reservoir computer.
Right.
Is it because I'm not sure. Like, so does it depend mostly on gamma or also on the density of the adjacency matrix? Like, is there a known like a relationship between the fading memory, like the time of it, like the time window, and some of those parameters?
Right. So it mostly depends on gamma here, a lot of it, because if you just take away this, right, this is an exponential decay of the system. So that's sort of gives some kind of idea of the time constant for like how long. It also depends on the, depend on the largest eigenvalue of A as well, a little bit. So I don't know if there's like a formal theorem or proof as to exactly how much. I think people have approximated and then said, there's some amount of finite memory, but yeah, that's called the echo state property in the literature if people are interested. So the idea is that because it's a dynamical system, it keeps the memory of past inputs up to a certain amount of time.
Okay, thanks. There's another question in the chat.
Sorry,
the choice of the equation for R of t bound the upper spectral radius, you still get global equilibrium for. sure I understand the questions.
Yeah, Brian, do you think you could
you elaborate, Brian?
Elaborate a little bit?
Just feel free to talk, Brian. Like, you don't need to use the chat.
Oh, I see.
Okay.
He's having an issue.
Yeah, we'll go back to that later on.
All right.
Keep going. Sorry, Jalen.
Yeah, so spectral radius is something you can actually choose to set. So you can just generate this random matrix, right? And then calculate what that eigenvalue is and then divide it by whatever you want to get your sort of largest eigenvalue. So then tan H is applied afterwards, I guess, if that makes sense.
Oh, and just for clarification, how big are the network you're talking about there? Like
Right. So in the previous to the application for the Lorenz system, it was anywhere between, I think, 500 and a couple thousand nodes. I've used stuff over, 5,000-6,000 is probably the largest you want to be fitting into memory. And then you can use like multiple reservoirs in parallel and stuff if you want to like scale it up.
Okay, thanks.
Yeah, no problem. All right, so the question is, how do we narrow this search space for hyperparameter selection? So instead of searching over this whole huge space, can we sort of narrow down that particular region to find good hyperparameters that give good predictions for the problem? And one thing, I don't know if I mentioned, these hyperparameters are very problem dependent. So if it works for one problem, it almost certainly won't work for a different problem. And this is even scaling up if you have like, 4 or 5 or 6 dimensional systems that you can just kind of scale up with the same dynamics. It will still like fail going from, say, 3 or 4 dimensional system to a 5 or 6 dimensional system. So that's just something I wanted to mention. So, sorry. The answer to this is through something called generalized synchronization. So I'm going to introduce generalized synchronization, talk about what it is, and then see how that can help us solve our problem. So synchronization, I guess everyone has a kind of general or basic intuition about what synchronization is, but the one I kind of visualize as I'm thinking about these problems is sort of Huygens' classic coupled pendulum problem, right? So he figured that he had 2 pendulum clocks and he coupled them together through some wooden board, and he showed that they would oscillate together in synchrony. And so if you think about this from a dynamical systems perspective, we can analyze this system in the joint phase space of the 2 clocks. And so this is the position and the momentum of the pendulums, right? So theta or theta dot, d theta dt, where theta is the angle. And so if we plot, say, theta 1 and theta 2 against one another, I guess this should be in the opposite direction. But the trajectories will traverse a line in phase space, or in the 4-dimensional space, this is the identity hyperplane. So if they're completely synchronized, they'll be on this line. And if they're non-synchronized, they'll be off this line. And so in kind of dynamical systems theory, we call this geometric object that the trajectories lie on is the synchronization manifold. So we can generalize this now to systems that are not identical to each other. So instead of 2 clocks, you can have your clock coupled to a laser or something like that. So completely different systems, different size systems, and chaotic systems. And so the general definition of synchronization in this case is that if you have some kind of input system U and a response system R, if generalized synchronization occurs, then there exists some function phi such that phi of R is equal to U. And that's the definition. And this should look really familiar, right? Because this is exactly how we train a reservoir computer. And actually a few years ago, Liu et al. Suggested that this was how reservoir computers work, that they work through generalized synchronization. And they suggested as well that recurrent neural networks in general operate this way. And so just to gain some intuition, if you plot, say, one of the variables from, say, your pendulum against the other one from your laser, right? In generalized synchronization, you no longer get a line for your synchronization manifold, you get some complex geometrical object. And you know, we didn't make this up, I guess I want to say. It was experimentally verified that you could couple, you know, completely random systems together. So there are questions on kind of the formulation of generalized synchronization. All right, so so now that we have our sort of description of generalized synchronization, let's sort of revisit our reservoir computer and show kind of how they fit together. So if we take our function phi now, say we found it, and we project the reservoir state into the sort of n-dimensional sized reservoir vector, right? The state of the reservoir into now the size of the dimension of u, you can actually see these two systems synchronizing together nicely. And so after some kind of transient period, they're completely synchronized. And this is because u is driving r onto this synchronization manifold here. So this is through this coupling here, we've got u, which is driving this system. And so just to sort of look at our training and forecasting again, we have u driving r into the synchronization manifold. Then we find this function phi by minimizing over parameters, such as, say, if you were doing a linear regression, this would just be some kind of output matrix multiplied by r. And then once you have this function, you can then drive your reservoir with your previous state, which keeps it on the synchronization manifold, ideally. And so the hope is that if you keep it on this sort of geometrical object that it's been driven to, it will give you a lot of nice properties, such as sort of physical forecasts and this kind of thing. And we'll get into that a bit later. So the idea is this for hyperparameter selection. If we could sort of find which parameters hyperparameters exhibit generalized synchronization with your input, then we can guarantee the existence of this function phi. So we see here in this upper panel, this is our sort of prediction like we saw before of the Lorenz system, we get a nice prediction. But if there's no generalized synchronization, then this function phi doesn't exist, right? So no amount of computational effort or ability is gonna like enable us to find it. And so we just get really bad predictions, really bad, it's just completely useless. And so if you could find a way to computationally efficiently find where it's has generalized synchronization and where it doesn't, then we could sort of narrow down this space and sort of count out those places in hyperparameter space where you won't have generalized synchronization. And so this computationally efficient method is called the auxiliary method.
Sorry.
Yes.
What was Z again here?
This was the, oh, sorry. This is the Z of the Lorenz system. So the Lorenz system has X, Y, and Z. X is like some kind of dimensionless convection, and then Y and Z are horizontal and vertical temperature. And so this was just predicting, I guess this was X and this was Z. But we were showing that.
And would we have, I guess we would probably have similarly bad results if we were also plotting for X, right?
Exactly, yes.
Okay.
Yeah, all of the variables are off.
Why doesn't it work not even in the training phase?
Right, because if there's no generalized so this is a, sorry, these plots are a projection, right? So we're taking the reservoir state and then projecting it through this function phi back down to the d-dimensional space of the input. And so what this is showing is that there's just no mapping between the reservoir state R and the input state U. if that makes sense.
And do we know, or did you already explain why there is no mapping? Is it?
Right, because so if we go back to generalized synchronization here, so this function phi only exists if there is generalized synchronization between the two systems. Right.
And sorry, one more. Why don't we have generalized? So how do you set because am I right to interpret that the generalized synchronization in the reservoir here, is it just the connections between the units in the reservoir, or is it something else?
So the synchronization is actually between the the driving system and the response system. So if those two systems were coupling them together by sort of unidirectionally coupling them by injecting the input or the driving term into the reservoir, right? So if we go back to our system, right? So this is a driven dynamical system, and it's being driven by this U here. And so if there is generalized synchronization, if these two systems can synchronize towards one another, then they converge onto this sort of attracting set, which is this synchronization manifold. Whereas where phi exists, right? But if there isn't synchronization, say this, the reservoir is unstable, right? Or it's chaotic or something like that, then, putting U in will not give us a deterministic output because it's not synchronized. And so therefore this function phi doesn't exist. We can't find it, and we can't use it to predict forward in time.
Okay.
I hope that made sense.
Yeah, I have more questions, but I think I'll wait to the end so that I don't delay your presentation.
Yeah, I mean, we have time, but I can finish this part, and then we can talk about it some more, and then I'll talk about how to get robust predictions after. So what I'm explaining here is the auxiliary method, which is a computationally efficient test for generalized synchronization. So the idea is that you create two identical reservoirs, which are RA and RB, just label them. And they have different initial conditions, but they have identical stimuli. And so if they converge together, then there's generalized synchronization between you and the reservoir. And this is computationally efficient because there's no training. You don't have to train the reservoir. You just have to kind of evolve this dynamical system forward, and you only have to test for a short duration. And so if you find generalized synchronization, this guarantees the existence of this mapping function, which is what you need to find in order to predict forward. So an example of this, and sort of showing an advantage of why we'd want to use that, is I used the reservoir computer to predict forward, or applied it to the shallow water equations, which are kind of a simplified Navier-Stokes equations that are a reasonable model for the fluid dynamics of the open ocean. So they're sort of a large system of coupled partial differential equations. In this case, it's 192 dimensional. So it's an 8x8 grid. Each grid point has velocity and height. And this is much bigger, right, than our 3-dimensional Lorenz system. And so maybe it wasn't, super concerning on the Lorenz system because it was pretty easy, or it's pretty small to evolve that forward. But here, this takes, say, 20 minutes on a cluster to actually train and then predict forward and evaluate the reservoir. Whereas this auxiliary method will only take 16 seconds on my laptop to show. And so what you get is a graph something like this. This is just a 2-dimensional slice, again, in parameter space. You've got the sigma and the spectral radius of the adjacency matrix. And you see that this blue region is showing this is where generalized synchronization occurs. And then these colored regions are, this is where it doesn't occur. This is where the two diverge. And so what you can do is just restrict your search, right, to places where you have this generalized synchronization. And also, just what is more, the reservoir has sort of usually been known to work best in the regions where it's what's called the edge of chaos in the literature, the edge of stability. And so you really only have to look at the regions sort of around this small area around where it's sort of transitioning from generalized synchronization to non-generalized synchronization. And so doing this, then we could simplify our search space to this narrow band and then find reasonable predictions here. So this is the, I guess, the curl of the velocity field for some particular point. We showed predictions.
Hey, Jason, looks like there's a question in the chat.
Oh, yeah, sorry, I can't really see the chat if I want to.
Yeah, I was just letting you finish the slide, but the question is like, how different are the different initial conditions for like RA and RB?
I just choose them sort of randomly when I do it, but it's shown that you can choose any different initial conditions because when it's under generalized synchronization, the conditional Lyapunov exponents, so those exponents are kind of negative, so it all converges to the the same trajectory, basically. Oh, Henry is applying. Yeah, so they do have to be in the same basin of attraction. I haven't personally run into issues with that happening, though it could. There is a sort of theoretical possibility that this test could give you sort of false negatives, I guess, if there is generalized synchronization, but they converge to different basins. So I guess the real way to do it would be to take a few more and change, but because it doesn't really matter that much, we can just take 2 for computational efficiency. Any other questions before I move on to the next problem? All right, so we've looked at how do we narrow down the search space for sort of getting good hyperparameters for a particular problem. And so we can narrow down that region, we can search that region, and we find some hyperparameters. But how do we know that those predictions will be robust, that they'll give us physical parameters, that it doesn't depend on the sort of random variations of selecting the adjacency matrix or the training data, and so on. And so that's what I'm going to talk about next, is how do you evaluate that you've got, you know, a good reservoir computer that you can apply to many different problems and sort of rely on. So why do we care, I guess, is the first point, right? So if we look at the left hand panel here, this is my left, you see that we get some reasonable predictions up to maybe 1 or 2 Lyapunov times. And so maybe from a perspective, if you only care about predicting 1 Lyapunov time into the future, that's all you really want to know, then you could say, well, it doesn't really matter that it kind of just goes off and stops giving physical, meaningful forecasts. You know, the seas start boiling or whatever a year from now, but we don't care. And I guess what I want to say to that is that, you know, if your reservoir is giving you these, or your forecast, your recurrent neural network is giving you these kind of weird forecasts like in the future, how do you trust it? How do you know that that's something that you can trust going forward? Whereas if you look on the right-hand panel here, you see that it diverges, you know, after some amount, but it keeps giving reasonably physical forecasts. And this is something we call attractor reconstruction. So the idea is that we want to get stuff that's looking like this and less stuff that's looking like this, even though we have reasonable forecast time here. So the way sort of, I guess, people do it or look at it is, you know, to guarantee this kind of robust behavior, you would want to take, you know, several thousand points initial conditions, which is here I've taken 4,000 starting initial conditions, and then just check those predictions here. And then I took multiple instantiations of this reservoir and check those predictions. And you can see that since the standard deviation between the means of these kind of Gaussians that fit these prediction times are pretty small, then that's a reasonable sort of assertion that this is a robust set of hyperparameters. But there are some issues with this, right? It's time consuming. You have to predict over thousands and thousands of points. It might not be possible if you have limited data. And so we're proposing another criterion here. Instead of doing this kind of analysis, what you could do is, instead of this kind of test set, we would say that a well-trained reservoir computer would want to reproduce the spectrum of Lyapunov exponents of the input system. So reproducing these Lyapunov exponents guarantees that the global error growth between the reservoir and the original system is the same. And because if the Lyapunov exponents match, if the transverse Lyapunov exponents away from the synchronization manifold are negative, that makes it very likely that the reservoir computer will stay on that attracting set, will stay on the manifold and give us physical predictions going forward. And so here in this panel, this is the prediction time. So you can think of those as kind of the Gaussians that you saw in the previous panel. And then this here, this curve is the largest Lyapunov exponent for the reservoir. And then this is the largest Lyapunov exponent for the input dynamics. And you see that when they match exactly, that's the period of highest prediction. And it's also where you get those like nice physical forecasts, because the reservoir stays on that synchronization manifold, even though it diverges from the original prediction or the original system, it stays and gives nice physical predictions, right? And one thing I wanted to say is that it's important that there are sort of well-established methods for calculating these Lyapunov exponents purely from time series data. So you can have your data, whether it's, I guess, pictures, a video of a cat, or in this case, a geophysical application. And you could then calculate those Lyapunov exponents from that. Any questions on this? All right, well, we can come back in a second. This is my last slide. So an sort of alternative interpretation of these matching of Lyapunov exponents can actually be seen if you calculate the fractal dimension of the synchronization manifold. So the fractal dimension is the dimension of the phase space trajectories in sort of embedded in space. So this is the Lorenz Attractor again. And it's got a fractal dimension of 2.06 because it's kind of slightly offset from the 2D plane if you embed it in the three-dimensional space here. And so if you calculate that fractal dimension for the reservoir computer, the trajectories of the reservoir computer, you see that the lowest dimension, the lowest fractal dimension corresponds with the highest prediction, as well as the most robust forecasts. And I've been trying to look at sort of what the intuition for this would be. And I think it's that if you add movement in extra dimensions, in extra sort of, you add sort of degrees of freedom, this is equivalent to adding noise into the system. And there's no extra information you're adding, you're just adding movement in those directions, which can kick the forecast off your manifold and give you less good predictions and less physical predictions. And so that's just kind of another way of evaluating and looking at, why do some hyperparameters give good predictions and why don't they? And the idea is to have then a nice physical prediction and a good prediction, obviously. So just kind of wrapping up this theory section here before Randall then goes into applications to neuroscience. So recurrent neural networks are, quite a good method of choice when it comes to time series prediction tasks, and reservoir computers, you can think of them as kind of simplified versions of more complicated recurrent neural networks, such as LSTMs or gated recurrent units or something like that. And so what you can do is you can use the auxiliary test to narrow down the hyperparameter search space when applying it to a new problem. So if you have like a huge, thousands of dimensions that you're trying to predict, and you have this massive reservoir computer, you don't have to spend time training on parameters that don't give you generalized synchronization. You can instead use the auxiliary test, which is nice and computationally efficient, see that those parameters are duds, and then move on. And then, so once you've found some good set of hyperparameters, you can use the Lyapunov exponents, that calculation, to give a rigorous evaluation criteria. If you say don't have a large amount of data, or it's too expensive to do that, you can then test, and then that will sort of suggest that your reservoir has good generalizable ability and give good physical predictions. All right, questions for me before we switch to Randall?
I guess there are no questions.
All right.
Alrighty. So Jason has covered the fundamentals and the theory behind reservoir computers and generalized synchronization. So I'm going to do some easier stuff to follow, hopefully, some more fun stuff where you should talk about some applications. Hopefully this will be less of a head scratcher. We're just going to cover some fun things you can do with the reservoir computer that our group has done. Oops. I have to click it. So first, might be an obvious question is, why would you want to apply a reservoir computer to neurons? It's a forecasting tool. So oftentimes, like, the weather is days in advance, but a neuron, its behavior is on the order of milliseconds. So why would I want to forecast something that I can blink and it's already going to be done? The purpose is more so less in the forecasting, more in the ability to model neurons. In the cases where we have large complex descriptions and mathematical equations of models of the neurons, we can instead, just based off of the data observed from experiments, we can imitate the behavior of those neurons simply just by modeling them with a reservoir computer. Alternatively, there's practical applications in machine learning. For instance, in machine learning, learning tools are learning selections, identifying numbers, or any type of supervised learning. The human brain does that significantly better. And so the better we're able to model brains, we could, in theory, maybe use a model of a brain based off a reservoir computer to improve the efficiency of machine learning tools. So moving on from some of the ambitions of this, we can move on to some proof of concept examples. We don't have actually full-size brains. We've done work on those of 10 to 11 neurons. These will be much smaller. We'll start with a single neuron, a very simple case of the Hodgkin-Huxley neuron. The Hodgkin-Huxley neuron was an equation invented in 1952 to describe the voltage between the cell membrane based off the sodium-potassium channels. And we'll be using this to perform 20 experiments. We won't be telling the reservoir what this equation is going to be. The reservoir won't know anything about gating variables or ion channels, but we will generate data from the equations of the Hodgkin-Huxley system, and we're going to feed that into the reservoir. And so we'll be using a hyperbolic tangent model that Jason has described previously, and this model will only receive the data, and we're going to use that data as well as our tools like generalized synchronization to try to make a good fit for these parameters. So the first thing we want to do is we want to stimulate our neuron. I have to make sure to go back for a second. Part of the equations. Oh, yes?
Yeah, so how do you said you're gonna use the Hodgkin-Huxley model and use it as an input to the 10H model? Is it gonna be you? What exactly are you doing here?
Oh, sorry. So I'm gonna integrate, randomly initialize the states of the model. So the Hodgkin-Huxley model, also known as the NKL model, that has 4 states, the voltage, and 3 gating variables labeled M, H, and N. We'll initialize them randomly. You can just choose anything for the most part. And we're gonna inject a stimulus. We're gonna inject a chaotic stimulus. We're gonna use the Lorenz 53 system, and we're gonna integrate it forward with a tool like Rangakata. And so we'll generate a full set of data, and this is what that full set of data will look like. So this orange curve is the stimulus. This is just the data taken from the Lorenz 53 system. It's just a nice chaotic signal. And we're going to inject this, into the voltage equation. And so we can generate all these nice spikes that now we're going to have a full training and prediction window from a full set of data that we can give this data to the reservoir. So what the reservoir will receive will be all this data. But it won't receive the equation, but we need the equations to perform the twin experiment. So hopefully that clears things up a bit. So like I said, so we have now 4 dimensions from the Hodgkin-Huxley model. We've had that data generated. And we also have the 3 dimensions of the Lorenz 53 model, at which we've only fed in the X dimension into the Hodgkin-Huxley equations. And so we can take all this data, all 7 dimensions, and we can feed this into the reservoir, or we'll perform our training and our predictions. So now that we have this data set, before we can make a prediction, we want to have a good choice of parameter selection. We want to be able to find a way to pick good hyperparameters that will give us a good prediction. So before we start using any sort of parameter finding tools, we want to find the generalized synchronization, because by constructing a generalized synchronization map, we can quickly and efficiently weed out where areas of bad prediction will be. So in this map, what you see here is I've varied the SR, the spectral radius hyperparameter, and the probability of non-zero values. And we varied these values such that we calculate using the auxiliary method what the auxiliary, or what the if there's an existence of generalized synchronization. And we do that by making a contour map of the log of the distances between the 2 starting points in the auxiliary method, which are randomly initialized at some faraway points, and they converge to very close to within a norm distance of 10 to the minus 13.
Oh, Randall, sorry. What's the size of your adjacency matrix, like in that case? It's a question on the chat.
Right. The size of I believe for this case it would be, I think I might have offhand chose 2000, but I think also in some methods I allow it to vary. I treat number n as a hyperparameter. So for this GS mapping, I believe I set it to 2000.
Okay, thanks.
Mm-hmm. But I will vary the number of nodes when I'm sweeping through parameters. So I can talk about that now on the next slide. So I have now a GS, a generalized synchronization mapping. So I've now, right. And so I have this map now, and the red regions are my good regions, because we can see the distance between the 2 vectors that in the auxiliary method where they converge to a very close point, to 10 to the minus 13 norm distance. So now we have a region that we're going to search through. And there's 2 ways that, and practice that I use to find a good parameter within this region. They're both significantly longer to perform than generalized synchronization, which is the benefit of performing GS in the first place. So now I have a smaller area to perform these more intensive methods with. So the first method is just a nice, clean, simple brute force method. We just sweep through a bunch of values. We just take some point of SR and we just slightly increase SR and repeat the prediction until we find something that's good. Alternatively, we also use a fancier tool. We use what's known as differential evolution. It's just a genetic algorithm. It's a nice tool that will try to take a range of parameters and slowly shrink them down to a small and smaller area where if we optimize a cost function, typically just the mean squared error. And so we perform these parameter fitting tools on the Hodgson-Huxley model, and we're able to get a pretty good prediction. So the reservoir computer acted completely autonomously. It only received data from the training window of the 4 dimensions of the Hodgson-Huxley model and the 3 dimensions of the Lorenz 63, which was stimulating the Hodgson-Huxley model. And we were able to predict for about 100 milliseconds or so. And so this ultimately led us to another thought of, well, how can we make this a little bit better? And in brainstorming this, we think about how in the lab, in biological lab, it's often the case that the stimulating current is something that's decided in advance. That's something that we know what that's going to be, whether it's being provided to the Hodgson-Huxley equations or it's being injected into a neuron from a wave function generator. We can know in advance what the stimulus is going to be. So we thought So we thought well, why don't, during the prediction process of the reservoir computer, why don't we provide what the stimulus is going to be at all times? So now what we do is during the prediction phase of the reservoir computer, the training has remained the same. Everything's remained the same, but what we're going to do is when we output our prediction, the 4 values from the Hodgson-Huxley equation and the 3 values from the Lorenz 63 system, we're going to toss out the Lorenz 63 values. That's the X dimension of it. Just to remind you, is operating as an injected current for the neuron that we're trying to study, and we're going to keep providing the true value. We're going to pretend that we're in a laboratory and we've chosen the current, the stimulus on a wave function generator, so we know what that's going to be, but we don't know what the voltage is going to be. We're going to train on the voltage, and we're going to train on the Lorenz 63 values, but then we're going to continue just to predict forward, while only not knowing what the voltage and the 3 gating variables are of the Hodgson-Huxley equations. So, like before, we made that change to the reservoir, but we want to, do another parameter fitting. But we've changed nothing about the training process. The GS mapping has remained the same. The input data from our 7 dimensions, our NAKL system, or rather the Hodgson-Huxley system, and the Lorenz 63 system, that's remained the same. So our GS mapping has remained the same. It's still of the same shape, if you remember from a few minutes ago. And so we can now perform the same type of parameter searching tools within this good red region of generalized synchronization. And now we get another good prediction. This time, instead of diverging from the true value at around the 100 millisecond mark, we're able to predict for the entire 200 millisecond prediction window. And ideally, it could possibly go on even further than that, but we stopped it at 200 milliseconds. So this has significantly improved our ability to use the reservoir computers to model the behavior of the neuron in relation to its stimulus and its gating variables. And so this led us to, I guess, our next thought as well. Okay, so we can model a neuron pretty well, with some errors. So let's add some complexity to this. So what we thought would be more interesting is to try to tackle a network of neurons. So here's a simple toy model. It's on a 3x3 grid. We have 9 neurons, still not enough to build a full brain, but it's still a nice proof of concept of how we could expand this model to incorporate more neurons with the long-term goal of building a full brain, which is probably quite a ways away to get to 10 to the 11 neurons. But this is a nice proof of concept step. So we have a nice toy model of 9 neurons. These are all Hodgson-Huxley models, or Hodgson-Huxley neurons. They're all identical, and we have these 12 synapses that connect each of the neurons, and we're going to inject a current into neuron 5. But to break up the symmetry a little bit, because we do use a nice simple model of a synapse, we're going to add some randomness to the equations, or to the specific to the parameters within the equations of the synapse. So the time constant, the conductivity, and the action potential of each of these synapses are going to have a little bit of randomness added to them. So that way we can break up the symmetry and we don't have 9 neurons all doing the exact same thing, which would be a less than interesting problem. So that's exactly what we do. Again, we take this is the X dimension of the Lorenz 63 system. We inject this into neuron 5, this guy, the center neuron. Oh, whoops, sorry. And we can generate a nice set of data. This is this is all 9 neurons. This is all their voltages acting in response to, oh, apologies, sometimes my mouse key disappears. So this is the voltage of the 9 neurons in response to this injected current, and they're all firing. And so they're firing in response to a presynaptic neuron flowing current into them. And so what we'll do, like just before us, we'll take a reservoir computer, we'll give it all the voltages from each of the neurons, all their gating variables. We're going to feed those into the neurons or into the reservoir. And we're also going to give the 12 dimensions from each synapse as an additional variable. So we add those to the reservoir. And so we add up to now a total of 51 dimensions that are being fed into this reservoir computer. And so now we have new data. It's completely different from before. So we need to find a new generalized synchronization mapping. Because we want to have another, we want to minimize our time trying to find a good prediction, a good set of hyperparameters. So we quickly find a new GS mapping. This time it came out a bit different. The SR values now have a cutoff of closer to 2, whereas before they were closer to 4. And then like before, we're going to use one of those parameter searching tools, like just maybe differential evolution, a genetic algorithm, or possibly just brute force grid searching within this good region. And in doing so, we're able to accurately predict and model the behavior of this 9 neuron system with some errors, but we're able to get the correct times when the spiking occurs. And this is the graph of the 9 voltages, starting with neuron 1, ending on neuron 9. And so the reservoir computer was able to model the behavior to a good degree of accuracy of what the toy model was doing. And so then it leads us to the next question. Well, that's still just only 9 neurons. It's not the most interesting thing in the world. It's not going to be able to be a full brain that can function like a functional organism attached to it. So what more can we do going forward? Well, there's increased complexity. The Hodgson-Huxley, the NHK model is very simple. There's far more complex models. There's also noisy neuron data from the laboratory, and there's also just more advanced, more complex synapses, larger neurons that could possibly be used in study with reservoir computing. But this was a nice proof of concept to see what we can do and possibly push further with reservoir computers. So that was just a brief little show of what kind of results we've been getting. I hope you've enjoyed dipping your toes into the reservoir computers today. If you have any questions for me or Jason, the floor is open to them now.
Thank you, Jason and Randall. So please, if you have any questions, just ask directly, or you can write them in the chat and I will read them to Randall and Jason if you're not unable to talk for some reasons. So there is a question. Did you use graph theoretic reservoir initializations?
I'm not sure what he means by that.
Could you elaborate?
The question. Maybe like some tools from graph theory for initializing the adjacency matrix, I will suppose.
Yeah, we just chose it to be random. I think it's called technically it was an Erdos, randomly.
Yeah, like this, the kind of Erdos-Rényi randomness, or maybe like Storgat's idea of randomness.
Yeah, it was an Erdos-Rényi randomness, I think.
Yeah.
But yeah, we didn't spend too much time sort of optimizing that or looking at that. There are sort of other studies as well looking at different reservoir initializations and structures.
I had a question about the training. I think when you said about training, you mentioned something about setting that phi function there. So was this also the training for that is also related to the, so is it also the linear regression that you mentioned?
Yeah, so we use linear regression for all of that.
Okay.
Yeah, so the intuition there is if you make the reservoir large enough, then you can sort of use linear regression to, you know, map from that large space into the smaller space of the input. And that's kind of your approximation. I think if you use nonlinear techniques to sort of fit that, then there might be a way to sort of shrink the reservoir size down, maybe even to the dimension of the system.
Any other questions? So I have a question. Did you try to use your method to predict the activity of a reservoir at different echo state network? So if you're like using your reservoir method to predict the activity of a reservoir?
Sort of a recursive reservoir. I didn't. Randall, did you did you try that?
I don't think I have. Not yet, at least.
Yeah, would there be is there an interesting sort of purpose for doing that? Are you thinking, Frederick, or?
No, it was just for like the recursivity of it, because usually you don't like, people don't really look at the activity of the random network, right? They're like looking more at the readout layers, and people don't really pay attention much to the activity of what's happening in the reservoir itself. But I don't really know much about enough about the reservoir to talk.
Right. So that's sort of why we were sort of analyzing the Lyapunov exponents and the sort of looking, yeah, at the fractal dimension of the reservoir attractor and sort of that kind of activity of the reservoir, because that was what we thought would then give us some more intuition about how to actually evaluate, you know, what's going on and yeah, what's happening in there.
I think we were asked to repeat the last question.
It was just if we'd use a reservoir to predict what was going on in a different reservoir or a different echo state network, and we hadn't.
Can you hear me?
Yeah.
Hello?
We can hear you.
Oh, okay. Okay. I had a question. You said there were some theoretical like edge case where the method could fail. And would that be like if you get a node bifurcation in your leaky integrator and you are able to step across from basin to basin?
Yeah, I haven't, maybe Henry is more qualified to answer exactly when the auxiliary method fails, but I haven't come across exactly when it would.
Okay.
I can give a try. If your dynamical system, in this case, the reservoir, has multi-stability, many basins of attraction, it is unlikely that you're going to be able to make statements about the generalized synchronization from one basin to another. There's some literature on that, but I don't think it's known. It's a good question, and I don't think the answer is known yet.
Okay. I've been able to make the nodes bifurcate and then get the trajectories in state space to go back and forth between basins of attraction. And generally the network kind of all collapses to like one trajectory again. It's pretty weird. I've been trying to sort that out myself. Thanks, though.
Yeah, thanks for the question, Brian.
Oh, did you guys try any smaller matrices? I know Bolt was able to do some kind of adjustment where he got down to like 25 by 25 reservoir matrix on the Lorenz 1963.
Yeah, we haven't been pushing those limits. So usually what we do is we find sort of region of generalized synchronization, and then we'll set an optimization routine, either like surrogate optimization or, as Randall used, differential evolution, and then let that kind of pick where the best hyperparameters would be, and then we evaluate it from there. So we haven't purposefully been like, okay, what is the best we can do with 25 when, you know, maybe a 500 or 1,000 dimensional reservoir would actually be better.
Usually when I set the bounds for differential evolution, I usually set the lower bound from the nodes at around 300. And it generally like something a little bit larger than that anyways. But I could always restrict it to something smaller.
Mm-hmm.
So, yeah, oh, sorry, go ahead.
Sorry, there was a question on the chat from Steve Penny, who wanted the reference for that sort of smaller reservoir. Do you know who did it, Brian?
Yeah, just put it on the chat if you can.
Oh yeah, Bolt. Okay.
There was a dynamical system of, I think it was Fields Institute Dynamical Systems focus on reservoir computing like a year or two ago, and Bolt spoke in it, and he, using his reservoir, he took advantage, I think, of some linear algebra and was able to make a linear version that was, he said he got down to 25 by 25, if I remember right.
Yeah, I'd be interested to look at that.
One other question. I'm sorry, I don't want to monopolize. I'm just excited that other people are interested in reservoir computers, so I'll shut up if needed.
No, you're fine. It's interesting.
You're welcome here.
Oh, it's awesome. One other thing I was wondering about was you had mentioned noise with the larger matrices, and I ran into that problem. And there was an ICANN paper from like 2012 where a guy did a bunch of experiments on different size reservoirs, and he found that there's, depending on the data set and the size relative to it, you can have really well performing small reservoirs, and then there's like a gap from like 300 to above n equals like 1,000, where they won't perform very well, and then all of a sudden they start performing again. Well, that was what his results were. And so that's why I was curious about the size of your reservoirs, because I've been working on reducing the reservoirs, and I found the same gap. It's kind of weird. So
interesting. So there's just like a drop off in performance sort of for medium-sized reservoirs.
The size of the reservoir is the biggest influence on the computational time. To smaller reservoirs would definitely be better if the prediction can hold up.
Yeah, I've been applying controllability matrices and been able to find small reservoirs, and they perform really well. And then when you calculate the rank, the larger reservoirs, it's very strange because the ones that perform well will have full rank, like 1,000 by 1,000. But then smaller, if you pick like a 300 by 300 and calculate the rank, it points to a smaller size reservoir that can be used. And I can get down to like 25, 35. And by n, and still get the same performance.
I see. Interesting. Yeah, that's very strange. Does anyone else have any questions, I guess, before we have a longer discussion?
I think.
Please go on. Like, it's okay. Like, to have a discussion. Like, if there is interest in reservoir, like you can monopolize the time.
I have a question that is more. So there's this paper from it's a neuroscience PI. So Susilo and Abbott in 2009 that used reservoir computing. At first was just training these output, just the output weights, but then they also had this version of it that they were training also the weights in the reservoir. Or I don't know if maybe you already know this. Do you know this study? No.
I might have read it. Well, go on and
yeah. I just wanted you to, actually this is more an open question. If you can comment a little bit on like this kind of approach when you're also changing the weights in the reservoir. How does this, I don't know, can you make any comment about like just a connection between your talk and this kind of approach? Yeah, plasticity. Brian asked about plasticity. Yes. So it's a paper in which you have the reservoir, and you're just trying to also predict functions in the output just from the output connections. So and they create a method that does that pretty well, better than a science paper in 2004 from Jagger and Haas. And then afterwards, they show that they can also use the same plasticity rule that they used for the outputs, but also for the connections inside the reservoir, and it also works. So I just wondered.
From Abbott, Jason, and Randall in a neuron. Like there's the link in the.
Right. Yeah, I see it. Yeah, I think we've done some tries of having to either optimize the weights within the reservoir by, say, gradient descent or something like that. I haven't actually that was sort of, it seemed like there was a lot of computational effort for very little gain, actually. And that might have been just the size of the reservoir. I would imagine, my intuition says, and Brian, maybe you can jump in, that if you shrink the reservoir down, more and more, then the actual, individual connections will matter more. And so if you have, say, a 25 by 25 reservoir, you might want to optimize those, and it might be more computationally feasible. In terms of plasticity, I think there it usually, it'll take it's a lot more computationally intensive, again, to sort of keep running that and sort of wait until the thing kind of settles in some kind of equilibrium or something like that, rather than just running it, training the output, and then putting it in. So when we were sort of, or at least I was kind of focused on starting to try to scale up these models to larger and larger, say, numerical weather prediction data sets, and it didn't seem like that was a fruitful direction. But if we do want to kind of minimize it, then I would say that a lot more effort would need to go into optimizing those weights.
I was just gonna say, yeah, I kind of like where this discussion is going. It's getting really interesting, and asking the questions of, how does directly modifying the internal weights relate to this sort of, this mapping, or this kind of synchronization. And I was kind of curious, Brian, you said that you looked at the controllability matrix. I don't know if Brian is able to comment on that.
Yeah, sorry. My bad.
No problem.
Yeah, I did. Basically, what I found is the controllability matrix points directly to the length of the echo state property, or at least a minimum length. And then if you check the rank, like calculate equilibrium points through the trajectory when I model it, in areas where there's like local maximum or local minimum in a oscillating signal, the rank lowers and then increases through longer straight stretches. So there's a certain amount of memory that a well-parameterized network is varying depending on what part it's looking at. Pretty weird, actually. I've been looking at it all morning.
That's very cool, though.
So I'd be interested to see if have you tried, actually, Brian, sort of shrinking those matrices down by this sort of looking at the rank, and then actually sort of using, I don't know, a gradient descent or something like that to optimize those internal weights?
Yeah, well, I have kind of a side project I'm working on. I'd be interested to talk to you guys about. Where I'm trying, I use a symmetric matrix, a random matrix, and then I symmetrize it. And and try and get like a good gap between the largest, the spectral radius and the second value. Seems to work well. And then I set up a neural network in PyTorch where I eigendecompose it, and then try and adjust the eigenvalues on the diagonal to get a better map. But there's still some tweaking that needs to go on with it. But yeah, I've been trying that.
I see.
I don't know if that
Super
answered
cool.
the question. I might have wandered off into space. Sorry.
No, I'd be interested in learning more about that.
Well, oh, what motivated your choice on the leaky integrator version? Because there's so many of them.
Yeah, it was just kind of, you know, I mean, you just had to choose one, right? I liked the fact that it was kind of simple, and you could write the differential equation form and the mapping. There was like a nice equivalence between them. And so, yeah, I don't know if you've seen that one is better than the other necessarily. I kind of got the impression that all of them sort of worked.
Yeah, I haven't tried any of the other ones. I'll write the one that I use, but yeah, there was a bunch of them, and I do wonder about the ability to model different types of signals based on the type of leaky integrator, like how much effect that would have to how you organize it and structure it. But what's cool is the leaky integrator kind of creates a non-saturating activation function. It's pretty interesting.
Right.
But I had to go, but I have to hit you guys up for coffee or something, or over at Mandeville or something.
Yeah, email me, and maybe we can. I'd be really interested to see like more in depth about what you're working on, and maybe how, if you can work together or something like that.
Yeah, it'd be cool to have somebody to talk to. All right, thank you.
All right, bye.
Take it easy.
Thank you.
Thanks for the great talk. Bye.
No problem. Bye, thanks.
So we have time for one more questions. Don't be shy.
I think I have one. I think it's more a clarification question. If you can explain a little once more so in the slide of the generalized synchronization, you said that, so the idea is that you can synchronize two chaotic systems. So if what exactly do you mean by that? If it's just two different initializations of let's say the Lorenz attractors, how exactly are they interacting so that they would synchronize, for example? And I think other point that you made was also that even if it's different chaotic systems, they would also synchronize. So how does that work?
Right. So yeah, how does that work? It's kind of magic, right? You think about the definition of chaos, and then you're like, how can that synchronize to anything? And the idea that if you say you take like two Lorenz systems, you can like couple them together through, say, the X variable. Like you can just kind of add a term to the X variable of one that takes in the other one of the other, if that makes sense. And then those two would synchronize in the sense that, well, actually, since those are identical systems, they would identically synchronize. But if they, say, even the Lorenz systems had different parameters, they could still synchronize, but there'd just be this function that would be coupling the variables between them.
Okay,
and
so the figure that Randall showed, in which there was, I think there was a plot of a Lorenz system and a plot of the Hodgkin-Huxley. Was that the synchronized? So because they seemed kind of, I mean, of course, they're completely different system, but roughly at least their peaks were synchronized. Is that what?
Right. So if you're injecting the Hodgkin-Huxley, I mean, maybe Randall, you want to answer this question, but if you're injecting the Hodgkin-Huxley neurons like with a signal from the Lorenz system, then you could say that like the Hodgkin-Huxley neuron was driven by the Lorenz system, and those two were synchronized.
Okay.
Do you have anything to add, Randall?
Well, I mean, I kind of think you said it there, but yeah, I would think so. I didn't test the two systems were exhibited generalized synchronization, but one system was driving the other, so that would be.
Okay.
If there exists a function such that if I could input the current, and you could exactly tell me what the voltage would be, that would be the case. Which I think you could probably make a strong argument that is the case, without having to do the explicit testing.
Okay.
Yeah, no, generalizing, it's a little bit unintuitive, I think, because you're no longer coupling, you know, pendulums together. Or Lorenz's, right? You're coupling to, in our case, a huge reservoir network with some other system. And you're like, how are those synchronized? But they're synchronized through this coupling function phi. And that's the idea.
Thank you. A great talk.
Yeah, thank you.
Thank you.
Yeah, thanks for a great talk, guys.
Yeah, no problem.
Thanks for coming.
Yeah, thanks for coming.
But thank you again. I think we're going to close it there. And
Awesome. Yeah, hope to see you in person soon.
Please email them. Like I'm sure they will be happy to talk more about reservoirs.
Right. I think they should have my email. Is that correct?
No, I was sending on BCC, so I'm not sure that